In the second example of modeling with projectile motion, we'll use this bottle rocket that is launched from the ground at an initial upward velocity of 39 meters per second. So what I'm going to do first of all here is figure out what equation we could use to model the general projectile motion, and then we'll work to use that equation to find some characteristics of the path of this projectile. So since we're dealing with projectile motion, just recall that the height of the object after t seconds of time is a quadratic function. So we're going to have a t squared, and then a t term, and then a constant, right? So this coefficient in front of the t squared needs to be involving gravity, and it's always negative half of the gravitational acceleration. Because this is in meters per second, back earlier in these notes here, about 9.81 meters per second squared is gravitational acceleration. So when you do negative half of 9.8, it's about negative 4.9. So therefore, we do need negative 4.9 to be the coefficient of the t squared here. And then the coefficient of the t term needs to be the initial velocity of the object, v sub 0. And we actually know that this is an upward velocity of 39 meters per second. So it means that the object's getting launched upwards. So it has to be positive, and then it'll be 39 meters per second there. And then finally, we want to add the initial starting height right here. And it's actually launched from the ground, which means it's at a starting height of 0. So we put a plus 0 right there for the starting height. So it's kind of unnecessary to write the 0, of course, but I'll just leave it there so that we understand that goes there, right, for the starting height. Okay, so a number of questions that now we just want to address about this bottle rocket that's being launched, right? So first of all, this is asking for when the bottle rocket will land in the lake. As you can see, it's being launched over the body of water there, right? Okay, so if it's going to land in the lake, that means it's going to hit the water, which means it returns to a height of 0, right? So we'd want to be able to plug in a 0 for h and then be able to solve that, okay? So if you plug in a 0 for h, you end up with this equation, and then you want to solve this for t. So you could, if you wanted to, you could use quadratic formula, but it turns out that actually you could kind of factor something like this where you've got the t squared term and the t term, because you'd be able to take out a t, but also, like, then if you took out not only a t, you could also take out, like, maybe just the negative 4.9, like, as a decimal from both of the terms. That would give you just a t right here. And then you'd have to divide 39 by negative 4.9. It's actually a not so nice decimal. It's like minus 7.959, that sort of a thing. Okay, so the decimal goes on forever, but this is actually really useful now, because now if this quantity times this with that quantity and equals 0, then either this quantity, negative 4.9t, must be worth 0, or this quantity, t minus 7.95, whatever, needs to be 0 for these two quantities to multiply and give the answer of 0, right? So if negative 4.9t were to equal 0, then you could divide both sides of that by negative 4.9, and therefore conclude that t equals 0. And then right here, if that were equal to 0, you could just add the 7.95 thing. So then t would be about 7.95. So it turns out that those two values of time in seconds would be the times where it's on the ground. And this first one right here should make sense because it's launched from the ground. So therefore, when the height is 0, the time is also 0. And then the time would be 7.95 when the height is again 0 when it hits the lake. So that would address and answer that question. And then this right here is asking for at what time the bottle rocket would be at a height of 45 meters. It's kind of, the same question, but it's just plugging up a height of 45 instead of 0, right? So now you could plug in 45 into the equation like this, and then try to solve this. So for something like this, you might want to use quadratic formula. You wouldn't really be able to get by with factoring. You got decimal and interesting numbers, right? So if you got a 0 on that side, you could do so by subtracting the 45, which would get you to this point. And then, then you could use quadratic formula to solve for t right here. So t would be equal to negative b plus or minus the square root of b squared minus 4ac And that's going to be all over 2 times a, of course. Okay, so just kind of simplifying this out right here, you're going to end up with negative 39 over 2 times negative 4.9, so negative 9.8, and then plus or minus. If you square the 39, you end up getting 1521, and 4 times 4.9 times 45 gives you 882. And because we were taking a negative times a negative times a negative there, that'll end up being a minus underneath that, and that'll be over the negative 9.8. Yeah, so let's kind of divide some of this out. We're going to get very decimally stuff, so I'm just kind of round a lot of this stuff right here. So this is about 3.98. Again, that's just kind of rounding it off. And then underneath the square root, you'd have 1521 minus 882. So you'd actually have 639 under the square root over negative 9.8. So if you square rooted 639, and then you divided that by 9.8, you'd end up getting a decimal that's about 2.58, roughly. Okay, so this is just approximate, right? So about 3.98 plus or minus 2.58. So if you plussed, you would get 6.56, and then if you minused, you would get 1.4. So at 6.56 seconds or 1.4 seconds, those would be the times where this happens. And what was happening here is that that's when it would be at its height of 45 meters, right? So it would hit 45, go higher for a while, then come back down and hit 45 again, okay? All right, and then this right here is asking us for the maximum height of the bottle rocket, right? Okay, so if we want to determine the maximum height for this bottle rocket, since the equation we have is currently in this form, negative 4.9t squared plus 39t plus 0 is in standard form, we know that the maximum height will occur at the axis of symmetry. So we're going to have to find the axis of symmetry first, which is, this is a quadratic in standard form. We'll have to use negative b over 2a. So t is going to be equal to negative of 39 over 2 times negative 4.9. So if you divide that out, it's negative 39 divided by negative 9.8. You get approximately 3.98 seconds is the axis of symmetry. So that's when it reaches its maximum height, right? But if we want to find the actual maximum height, we want to then plug in, basically 3.98 into this. So you want to do h of 3.98. So that'd be negative 4.9 times 3.98 plus 339 times 3.98, and evaluate that. And then I forgot to write the squaring right there. Okay, so I'm going to square the 3.98. So it gives you 15.8404. Times that by negative 4.9 and add whatever 39 times 3.98 is, which is 155.22. So yeah, you can just, of course, type this all in a calculator. And it comes out to be about 77.6, just kind of rounding that off. This was in meters, so that right there would be the highest height that this bottle rocket's going to be able to reach, right? And then the last question right here is being able to find what the height of the bottle rocket is after a tenth of a second, which just means that time is going to be equal to 0.1, right? Or 1/10 of a second. So that really is just a matter of plugging in 0.1 for t, right? So you just got to do negative 4.9, square the 1/10, and add 39 times the 1/10, right? So if you squared 0.1 and then you times it by negative 4.9, you end up getting negative 0.049, and then that's going to be plus 3.9 is a tenth of that. So you add that all together, and that gives you 3.851. So that would be the number of meters after 1/10 of a second